Hi, and welcome back to the lab. If you haven't already, go ahead and hit that subscribe button down below to ensure that you stay up to date with all the information and content coming from the lab. Today is a Maker Basics video. Next month's major project is going to be a self-balancing robot, as I had announced in the channel update video. So, we're going to need to use motors in order to drive the wheels, obviously. I figured this would be a great time to talk about stepper motors, introduce some of you to what a stepper motor is, when you would use them, how they work. A lot of people for self-balancing robots use a standard DC motor. I think for our needs, the precision of the stepper motor will be very beneficial. So lab code up. We're going to learn something today. Alright, so this is a stepper motor. It's a standard NEMA 17, which is almost the most common, I think, stepper motor out there. They're in almost every 3D printer. A stepper motor varies from a normal motor in that every time you apply current, it moves a very precise amount, usually 1.8 degrees, unless you were doing something called microstepping, which we'll get back to later. And the way it does this is kind of unique. And I'm going to have to draw this, so forgive my drawing. So you have your standard stator in the middle, right, which we'll draw as a circle. And all around the stator we have different magnetic, a different pole. So wherever there is a black line, let's say that is magnetic north, and wherever there is a gap, that is magnetic south. Okay, now the stepper motor has individual coils that come in very much like this. Okay, so by varying which direction current flows through these coils, you change the polarity of that magnetic field. And the stator will jump to meet that polarity. You can obviously do microstepping magic, which is something that's a little beyond what I'm going to talk about here. We're going to just deal with full step because it's easier to explain. Microstepping magic is usually handled by another controller for the stepper motor, which we'll show you in a little bit. To show you what the action of a stepper motor actually looks like once it's going, I have this one hooked up. If I turn on the motor's power supply, I don't know if you can hear the hum that's going on back there, but it's definitely a slightly louder stepper motor. But it's also on an aluminum plate, so that might be what's going on too. Alright, so let's dive into how we are controlling this stepper motor. Okay, so the way that the stepper motor actually works. If we apply a current coming through in one direction here, and then the other direction here, one of these will be north, one of these will be south, and the stator will jump to move. Now, these magnetic poles these magnets on the side of the stator are not linear. They're offset as you go down the stator, right? So every time you alternate these, the stator will chase it. And the way that this gets alternated is with pulses. You'll notice that the motor that is currently running right here has 4 wires coming in. Right, now I've drawn 4 poles here, but in all honesty, these 2 are connected and these 2 are connected. So the 4 wires going into the motor are actually A1, A2, B1, and B2. So while this is running, the controller is pulsing and alternating these fields many times a second to make it spin. But one of the side effects that we get with this type of control is that I know that every time I give it current, it's moving 1.8 degrees. So I have my oscilloscope set up on my laptop over here. So if we take a look at that, you can see the second pulse, channel 2 and channel 1 are the 2 coil feeds going to the actual motor. Channel 3 is the pulse going to the controller, and channel 4 is the direction that is being requested. So you can see that when the direction changes, the offset from the signals for 1 and 2 change. And that's what actually causes the direction to flip. Also, every single one of the square waves here is causing the stepper motor's output shaft to move by 1.8 degrees. Now, there is the caveat of microstepping. Right now, this is in full step mode, which means every time you send it a pulse, you get 1.8 degrees of movement. With microstepping, we can do 1/4, 1/8, 1/16, and 1/32 of a step. Now, the math of how this happens is a little bit beyond a basics level video, so we're just basically going to ignore it. And we're going to drop down, we're going to take a look at the circuit that we have running here. Now, I apologize. The circuit that I have running here looks really complicated, but a lot of that is for the oscilloscope so that we can see what is going on with the actual stepper motor. So it is obviously possible using something along the lines of an H-bridge to directly control a stepper motor. Obviously, you're only going to get the full step mode. If you do that, it's really convoluted and requires a lot of parts to work with, and to be honest, buying a stepper motor controller is generally about the same price once you've paid for all the parts. So that's what we have here. On the breadboard, what we have going on is our standard Arduino Pro Mini that we use for just about everything. Alright, so because the project in April is definitely going to require microstepping, I've chosen to use the A4998 stepper motor controller. This does is it takes 3 pins from the Arduino, which is enable, direction, and a step pulse. And as I mentioned before, if we look over here at the oscilloscope, channel 4 is direction, channel 3 is step pulse, and the channel 1 and 2 are the actual motor outputs. Right, so you can see it shifting there. The other pins are motor voltage in, because it's obviously going to be a lot higher than 5 volts. So in this particular case, I am using 9 volts to turn this. This controller can take up to 36 volts, but if you're going to go up anywhere above, I'd say 12, you probably want to start using a heatsink. Right now, this has been running for a while. There's absolutely no heat on the chip at all. So we have enable tied to digital pin 13. We have step tied to digital pin 12, and direction tied to digital pin 11, or IO pin 11. Those channel into here, we're feeding the 9 volts into, if we go back to the diagram here, we're feeding the 9 volts into a V motor and ground. The B1, B2, and A1 and A2, if you look at the motor itself, you find that there is a resistance across the coil. Those 2 wires are connected. It is an easy way if you haven't bought the stepper motor brand new and you salvage it out of a 3D printer or a normal printer. That is a good way to get that done. I want to give a special shout out to How to Mectronics. It's a great YouTube channel. Watch it all the time. Much better artist than me. I wired it up exactly the same way he did. So if you take a look here, you can see the sleep and reset are shorted. Some tutorials say you don't have to do this. I did. I'm currently feeding the motor 9 volts, and while it's moving, it's drawing about 450 milliamps. When it's not moving, it's drawing about 0.04 amp. If we take a look at the source code that I came up with for this, so as you saw, the schematic was pretty simple. The demo application is even simpler. You can see that I have a bunch of defines up at the top here. I like defines. A lot of people in a lot of other tutorials will use constants. Constants take memory when it's running. Defines don't. I always use defines because they get replaced by the compiler as opposed to being held in global memory. So we have a define for the enable pin, a define for the step pin, a define for the direction pin, a define for what is clockwise direction and what is counterclockwise direction, and the degrees per step. Okay? So when we set up, we set the direction pin, the step pin, and the enable pin as outputs. And we set the enable pin just to enable the circuit. Now with a simple program like this, it probably would be smarter just to tie the enable pin up here to ground, because we're not changing it all in this particular application. But when we write our class that handles the stepper motors for the self-balancing robot, there may be times where we want to be able to disable the motor. And one of the caveats for new players with stepper motors is while this controller is enabled, you will not be able to move this motor by hand. It will fight you. If you want to be able to move it by hand, you then have to disable the motor, especially if you want your circuit to still be on. So we're going to want that level of control over our robot, so I left it in the base code here. Then what I did is I created a function called rotate. Rotate takes in the number of degrees I wanted to rotate, how long I wanted to delay between each step, and what direction I wanted to rotate in. So as you can see, I'm asking first for 360 degrees with 1 millisecond pause per step, and the stepper direction of clockwise. I'm then waiting 2 seconds, and I'm asking it to rotate 360 degrees again with that 1 millisecond of a pause in between pulses, and this time to rotate counterclockwise, and then again wait 2 seconds. If we look at the motor, you can see that it's doing pretty much that. Okay, so basically what the rotate function does, right, is we take in the number of degrees we want to rotate, the delay per steps, and the direction. The first thing we do is we define a double, because as soon as we do a division, it's going to be a double, not an integer. We divide the number of degrees that we want to move by the number of degrees per step. So we can figure out how many steps we have to take. Then we digital write the direction pin based off of what was handed to us for which direction we want to rotate. Then we enter a for loop, right, where we iterate through the number of steps that we have to go through. Now, because we're now using it to compare against an integer, we're going to lose the other precision, and there's rounding that gets involved. For our application here, don't even concern yourself with it. It will be accurate enough for what you want. And then we write the step pin high. We delay the delay per step, and then we write the stepper pin low and delay the delay per step so that the controller can see the difference between them. So now, when all of this is running, let's take a look at the oscilloscope here. And you can see what we have when the pulses are sent is a nice square wave. Let me take the sweep off. And you can see when the pulses are sent, channel 1 and channel 2, as I've mentioned earlier, are the two coils in the motor. Right? And you can see the polarity changing with the direction change. Channel 3 is our step pulse, telling it to step. Channel 4 is the direction pin. So when it's low, it's telling it to go in one direction. When it's high, it's telling it to go in the other. Now, obviously, when all four stop there, it's because the motor has been told to stop, and we're in that 2-second delay sleep. So when would you use stepper motors? I mentioned before that they're often used in 3D printers. Up until recently, a few years ago, they were used a lot in printers too, but now they tend to use an encoding strip, right? Because standard DC motors are cheaper, and it's easier just to encode them. And I guess they don't need the precision that they used to. I don't know. But you used to be able to salvage stepper motors out of just about everything. Even hard drives used to have stepper motors. Now they've got no stepper motors in a hard drive. In a CD-ROM, I believe there's still one or two for the actual head movement. But yeah, anytime you need absolute precision for movement. A stepper motor is generally what you want, especially if you need it to rotate more than 360 degrees. We are going to use them for the self-balancing robot because I'm going to need to very precisely control some wheels. Now, most self-balancing robots use standard DC motors and just use a feedback loop with the sensor to try to determine where they are, but I find that oscillates a lot. And I think the actual stepper motor would be a lot more precise and give us a lot more control over what we want to work with. But all in all, that is pretty much all there is to say about how to deal with a stepper motor using an A4998 controller. I want to thank you for joining me in the lab. I hope you learned something today, and we'll speak again soon.